Hi everybody, what's up? Welcome back to my cat math tutorial channel. Daniel's here and today I'm making my second video in financial mathematics and exam FM preparation. And my lesson today will be talking about time value of money. So our last lesson we have learned about different type interest rate and we have learned how to compute present value and accumulated value. Today we are going to compare investment money that is deposited or withdrawn at different time. So our objective today, firstly, I'm going to introduce the time value of money. Then I'm going to introduce time diagram as a tool to solve some problems of interest rate. And then lastly, I'm going to go over two type of problems that we are going to see very often in the actual exam. So firstly, time value of money. So why does money have time value? Let's look at this example. Suppose that deposit made today can earn 5% effective rate over the next year. Which would you rather have, $1,000 today or $1,050 in a year? So we know that using 5% effective interest rate, $1,000 today can accumulate to $1,000 times 1.05 in a year. So that means $1,000 today or $1,050 a year later will be the same. Or another way to think about it is like $1,000 today is worth more than $1,000 a year from now. It's just like, for example, today somebody borrow you $1,000, and then 10 years later they return you $1,000, exactly $1,000. So this example, you are losing money because $1,000 today you might it might be enough for you to pay for rent and eat in 1 month, but $1,000 in 10 years later it might not be enough to afford the rent. So that's why like money does have time value. And to compare the time value of money deposited or withdrawn at different time, we need a tool that is equation of value at a common comparison date. So to understand the tool better, we are going to look at the second example. So equation of value at a common comparison date. Situation 2, suppose you want to fund $5,000 in 3 years. For example, you want to have 5,000. You are raising a fund for your college. Like right now you are at grade 10 and you are funding money for your college. So your target is to have 5,000 in 3 years. So today you are making a deposit of $8. Then a year later you making a deposit of double of what you have deposited today. So if we assume that the effective rate is 6%, how much should we deposit today and how much should we deposit a year later? So now we are going to set up the initial time. So let's say today is the initial time t equal to 0, and our target is to attain $5,000 total accumulated value 3 years later at time t equals to 3. So if we look at the first deposit, our first deposit is $8 and it is deposited at time t equals to 0. So at time t equals to 3, the money that the first deposit will accumulate to X times 1.06 cube. And the second deposit is deposited at time t equal to 1. At time t equals to 3, it will accumulate to 2x times 1.06 squared because 2 years later. So now we expect to have 5,000 at time t equals to 3. So that means we expect that the accumulated value of all deposits that we have made should be the same as $5,000 at time 30. So we have an equation that is x times 1.06 cube plus 2x times 1.06 square is equal to 5,000. And this is just a very simple linear equation. So we solve for x. X is $1,454.24. So here's the thing. Conclusion. The time value of 5,000 in 3 years is the same as the time values of the combination of $1,454 today and $2,908.49 next year. And here, this example, we use in comparison day is 3 years from now at t equals 30. One question, what if we choose different comparison date? Let's say we choose comparison date 10 years later from now. So it's like t equal to 10. So suppose we choose the common comparison date at 10 years from now, t equal to 10. So we look at the first deposit. The first deposit, x, is deposited at time t equal to 0. So 10 years later, it will accumulate to x times 1.06 to the 10. And the second deposit, 2x, is deposited at time t equal to 1. 9 years later, at time t equal to 10, that deposit will accumulate to 2x times 1.06 to the 9. And our target is $5,000 at time t equals 3. 7 years years it will accumulate to 5,000 times 1.06 to the 7. So at this situation, we have using comparison date 10 years later from now, we have a new equation. X times 1.06 to the 10 plus 2x times 1.06 to the 9 equals to 5,000 times 1.06 to the 7. So that's the new equation, and solving this equation we have the same answer. X is $1,454.24. So that is about time value of money. Now we are going to use time diagram as a tool to solve some complicated problem that is involving many deposits and withdrawals at different times. So time diagram, first of all, this definition. A time diagram is a line of time visualize how deposits and withdrawals are made at different time. A time diagram is useful in solving problem of compound interest. So suppose you want to fund $5,000 in 3 years by making a deposit of X today and a deposit of 2X 1 year from now. If the effective rate is 6% per year, determine X. So our time diagram would be, first you have to define the deposit. Here we have two deposits, X and 2X. In the withdrawal, we have one withdrawal, that is $5,000. So here's how we set up the time diagram. So we are first making a line look like the real line. And then we mark the initial time 1, time 2, time 3. And then here we are going to mark the deposit and withdrawal. One thing you have to pay attention here, deposits should be in one side and withdrawal should be in one side. So X and 2X should be in the same side and 5,000 should be in the other side. And here on the left hand side we have years. That means the periods of interest is 1 year, because from time 0 to time 1 that is 1 year. So here if we use time 0 as a comparison day, X is still X. 2X, when you bring it back to the time 0, that means 2X is the future value after 1 year. So how much should you deposit to have 2x in 1 year? That should be 2x times 1.06 to the negative 1. And 5,000 times 3, bring to times 0, it should be 5,000 times 1.06 to the negative 3. One thing you should pay attention here, if you want to bring the money forward, you multiply it with 1 plus I to the power of n. That means where n is the number of steps. If you want to bring the money backward, you need to time with 1 plus I to the negative n, where n is the number of steps. For example, here, x at the time 0, so you bring to times 0, you don't have to multiply anything. 2x from times 1, you want to bring to times 0, you have to multiply 1.06 to the negative 1 because it's go backwards one step, one period. 5,000 at time t equals to 3, you want to bring to times 0, you have to multiply with 1.06 to the negative 3. That means go backwards 3 steps, 3 periods. And here we are going to use a new notation that is v equal to 1.06 to the negative 1. So we rewrite the equation. X plus 2x times v is equal to 5,000 v cubed, where v is 1.06 to the negative 1. Here, please make sure that you know this notation. V represents for the inverse of the accumulation function. So for compound interest, 1 plus I is the accumulation function. So V is 1 over 1 plus I, or 1 plus I, the whole thing to negative 1. And here I is 6%, so we have 1.06 to the negative 1. So that is how we use the initial time as the comparison day. Now suppose we use different time. Let's say we use time t equal to 1 as comparison day. So x at time 0, you have to bring forward one periods. So it's x times 1.06. 2x from time 1, we stay at time 1, so we don't have to times anything. 5,000 from time 3, go back to time 1, we have to go backward 2 periods. So it's 5,000 times 1.06 to the negative 2. And using v notation, we have x times 1.06 plus 2x equal to 5,000 v squared, where v is 1.06 to the negative 1. So that's how you make the time diagrams. And time diagram has some properties. Here is the complete time diagram. The first time diagram, I ignore the arrow here and the interest rate because the problem is quite simple. So I don't need to mark 5% and the arrows. However, the complete version of time diagram should have arrow like this and the interest rate. So the first property of time diagram is deposit and withdrawals are placed on opposite sides of the timeline. So here, for example, you see 1,000 and 2,000. They are in the same side, and x and 2x, they are from the same side. So that means if x and 2x are deposit, then 1,000 and 2,000 is withdrawals, and otherwise if 1,000 and 2,000 is deposit, then x and 2x is withdrawal. Next, to the left of the timeline, the interest periods is noted. So here, for example, a year, that means 1 year is 1 period of interest. So if you look at from 0 to 1, from time 0 to 1, because here we're using year as the interest period, so that means from 0 to 1, that is 1 year. The effective rate of interest for 1 period is marked off right here. So that means like for 1 period is 5%. 5% for 1 period. So if we move from 0 to 1, we multiply with 1.05. If we go from 1 back to 0, we multiply with v, where v is 1.05 to the negative 1. One more properties, a vertical arrow. The vertical arrows right here is placed at the comparison day chosen. That means which day we choose to be comparison day. So here in this problem, we choose time 0 as the comparison day. If we mark the vertical arrow as time 5, that means we are using 5 as the comparison day. Example. Situation 3, deposits are made on January 1st and July 1st of every year from 1995 to 2000 inclusive. The initial deposit is $100 and its subsequent deposit increases by $50. What is the accumulated value of deposit on January 1st, 2001 at a nominal rate of interest 5% compounded semi-annually? So here's the thing, deposits are made like twice a year, on January 1st, July 1st, and then January 1st, July 1st, and so on. So on the time diagram, we are not using 1 year as the interest period, but we are going to use half year. And here the deposits are 100, 150, 200, and so on, because the initial deposit 100 and then increase it by $50. And the question asks for accumulated value of deposit on January 1st with the nominal interest rate. So here the question gives you nominal interest rate, not effective rate. So what you have to do is find the effective rate for each period. So now let's look at the time diagram. Right here we have 1/2 years. That means the period of interest is 1/2. That means from time 0 to time 1 is half year. It's not 1 year. So it's from January 1st to July 1st of 1995, and then go up one more period. That means one more 6 months, and so on. 2 1/2. The reason why we have 2 and 1/2% here, because we have nominal interest rate is 5% compounded semi-annually. That means in a year, we are going to have 5% interest rate, but then because compounded semi-annually, that means twice a year. So each time the money is compounded, you got 2.5%. So that's why 2.5% is the effective rate for 1 period. So in 1 year, from time 0 to 2 is 1 year. The effective rate is 5%. You see that? Okay. And we have one more thing to pay attention here. That is, the question said, what is the accumulated value? Usually if the question asks for accumulated value, that means at the end, at the last time on the timeline. If the question asks for present value, is actually asking for time 0. So pay attention to the word accumulated value at the end and present value at time initial time at time 0. So here, because the question asks for the accumulated value of deposit at January 1st, 2001, so that means at time January 1st, 2001, that is the comparison day. So we mark a right arrow right here, and the question asks for accumulated value. So everything we need to bring to time 12. So let's look at the first deposit, 100. 100 from time 0 to time 12. That means we have to move up 12 periods, 12 steps. So we are going to multiply with 1.025 to the power 12. And similar, from 150 at time 1 to time 12, we move up 11 steps. From time 2, deposit 100, move up 10 steps to time 12. And then we are going to combine them all together. So we have an equation as the follow. The first term, 100 times 1.025 to the 12, that is the accumulated value of the deposit 100 at time 0. bring to time 12. The second term, the deposit 100, so $150 times 1.025 to the 11 is the accumulated value of the deposit invested at time 1 to time 12. And similarly, the last deposits, we have $650 move up 1 peters. So we have 650 times 1.025, that is the accumulated value. And then we can use our calculator to find the answer. Next, problem involving an unknown time. So as I said, like in financial mathematics about time value of money, we have two type question that we are going to see very often, very common in the actual exam. The first problem is when we don't know about the time, and the second problem is when we don't know about interest rates. So here the first type. For the problem involving unknown time, we have two methods of logarithm and methods of equated time. So I'm going to go over the first method. Situation 4. Suppose you deposit $500 in a fund at 4% effective. How long does it take for the fund to grow to $2,000? So here we have $500, and that is the money that we deposited at time 0. And we know that at a certain time the money will grow to 2,000. So the question asks for time. So this is the problem when we don't know the time. So we say T is the the time it takes for the fund to grow to 2,000. So $500 deposited at time 0, 2 times T will be accumulated to 500 times 1.04 to the T. And because we expect to have $2,000 at time T, so it's equal to 2,000. And this is an exponential equation problems. So we are going to solve for T. First, we divide both sides by 500. We have 1.04 to the T is 4. Then we take natural log both sides and solve for T. So T should be equal to natural log of 4 divided by natural log of 1.04. And that is 35.35. So it's around 36 years. So conclusion. It takes up to 36 years for the fund to grow up to $2,000. So that is the first method. Now we are going to the second method of equated time. This method is the method for determining an approximate value of time t using symbol arithmetic. So arithmetic here is just t bar, that means the arithmetic mean is equal to summation of di times ti over summation of di. Here is similar to weighted mean, and di here is the deposit mega times ti. So if suppose you have 5 deposits, then we have d1, d2, d3, d4, d5 at time t1, t2, t3, t4, and t5. So this is how we've find the approximate value of time t using symbol arithmetic mean. Now let's look at an example. Situation 5. Suppose Mark is scheduled to make 3 payments as follows. Time due. At the first years, 1 year later from now, he had to make a payment of $5. 3 years later from now, he's had to make a payment of $1. And 10 years later, he had to make another payment of $15. So the total payments he needs to make is $21. So now Mark and the other party agree to make only one single payment instead. So that means instead of paying $5, $1, and $15 as scheduled, Mark and the other party agree to combine them into one single payment of $21 at time t. So the question asks what time he should make payment to have the same time value of money. So the solution, firstly, we think about the equation of time. And in this situation, we let B be the time when the single payment is made. So using comparison time t equal to 0, we have 21v to the t, because 21 is made at time t. So when you bring to time 0, you have 21 times v to the t equal to 5 times v plus vq plus 15v10. 5 times v, because 5 from time 1 we bring to time 0, so we have to multiply with v. $1 from time 3 go to time bring to time 0, you have to multiply with vq. And $15 from time 10 you bring to time 0, so you have to multiply v to the 10, where v is 1 plus I to the negative 1. So here when you write out this equation, you realize that this equation cannot be solved because we don't know v and we don't know interest rate. So sometimes the equation of time fails to find the approximate time t. That's why we need another solution, that is method of equated time. In this method, we are going to use arithmetic mean. So we are going to multiply its payment with their time due, add them together, and then divide it by the sum of payment, the total payment. So here 5 is the first payment at time due 1, 1 is the second payment at time due 3, 15 is third payment at time due 10. So we take 5 times 1 plus 1 times 3 plus 15 times 10 divided by 21 total. So we have the answer is approximately 7.52. It's around 7 years later we should make the payment of $21. So that is the problem involving unknown time. Now we go to the second type, that is problem involving unknown interest rates. So here's the thing. Situation 6. At what interest rate of at what effective rate of interest will a payment of 1 now and 2 in 1 year accumulate to 4 in 2 years? So that means we are going to make 2 payments, 1 today and 2 1 year later, and we are going to use a comparison time 2 years later. So let I be a known effective rate of interest, and using comparison time t equal to 2, we have the following equation. So the first one, $1 from time 0 bring to time 2, that means 2 years later, is 1 times 1 plus I whole square. And $2 1 year later accumulate to 2 times 1 plus I when at time t equal to 2. And we are expect to have $4, so that becomes 4 on the right hand side. And now we are going to solve this equation. You notice that this equation is quadratic like, but it's not quadratics. So this is a quadratic like equation. So we are going to change variable. We are going to set a new variable. U is equal to 1 plus I, and then we obtain a quadratic equation. U squared plus 2u minus 4 equal to 4. And solving this equation, we are going to have 2 solutions, but one negative and one positive. However, u is 1 plus I is positive, so u cannot be negative. So we are going to take only the positive root, as u is positive. So u is negative 2 plus square root of 2 squared minus 4 times 1 times negative 4, the whole thing divided by 2 times 1. This is just basic solving quadratic equation in college algebra, so I don't think I have to mention how to solve quadratic equation. So u is around 1.236 years. So the answer I'm sorry, 1.236 AUs. So we are going to set 1 plus I equal to 1.236, and we solve for I. So I is about 23.6%. 23.6%. So that's the answer. So for the problem involving unknown interest rates, we really have to solve the a polynomial equation. And I consider this problem is the hardest one in time value money because the question requires you know how to solve quadratic equation. So compared to the other type of question, which is unknown time, this question is a little bit harder. So that is about time value money. Now we are going to try some problems. Problem number 1. David can receive one of the following two payment streams. The first stream is $100 at time 0, $200 at time n, $300 at time 2n. The second method, the second option is 200 at time 10. So the question is, at an annual effective rate I, the present value of two streams are equal. Given v to the n is 0.75941, determine I. So the question gives you two option of payments, and they give you the present values of two streams are equal. Remember, present value, that means comparison time is 0. So we are going to bring everything to time 0 to compare. So first look at the first payments. The present value at time 0 should be first 100 at time 0, so we don't have to multiply with anything. From 200 at time n, bring to time 0, we have to multiply with v to the n. 300 at time 2n, bring to time 0, we need to multiply with v to the 2n. And because v to the n is given as 0.75941, so we have present value of the first payment is 100 plus 200 times 0.75941 plus 300 times 0.75941 square, and that's equal to $424.89. Now we look at the second payment. At time 10, we have a payment of 600. So bring it to time 0. You should multiply it with v to the 10. So present value is 600 times v to the 10. And because the question said the present value of two streams are equal, so we are going to set the two present value equals and then solve for v. So 600 v to the 10 equals to 424.89. So v is 0.966, and from v is 0.966, we have 1 plus I is 1 over v, so it's 0.966 inverse. And from here we can find I by subtract this by 1, so it's 0.035, so it's about 3.5%. So answer A. So that's the first question. So when you deal with the problem using time value money and interest rate, try to choose a comparison time, and then bring all the payments or withdrawal to that time to make comparison. So that's problem number 1. Now we go to problem number 2. Joe deposit 10 today and another $30 in 5 years into a fund, paying simple interest of 11% per year. So this is simple interest rate. Remember, on the first lesson we have two type interest: simple interest and compound interest. For simple interest, the accumulation function is 1 plus it, not 1 plus I to the t. It's 1 plus it. So pay attention here, because many times you will have mistake using 11% as effective rate. And Tina will make the same deposits, but 10 will be deposited end use from today, and $30 will be deposited 2 years to end use from today. Tina deposit earn an effective rate of 9.15%. So here Tina using effective rate, not simple interest rate. At the end of year 10, the accumulated amount of Tina deposits equal to accumulated amount of Joey's deposits. Calculate in. So here the question said at the end of 10 years, so they already indicate the comparison date is 10 years from now, right? And the question gives you 5 option choices. So solution, first we look at Joey's account. Joey deposit 10 today and another $30 in 5 years, and using simple interest rate. So the first $10 from today go to 10 years later, that means t equal to 10. So we use 10 times with 1 plus 10 times I is 0.11, because the accumulated accumulation function of simple interest is 1 plus t times I, or I times t. So here 1 plus 10 is t and I is 0.11. And then $30 is a payment 5 years from now. So at time 10 is go up 5 more steps. That's why we have 30 times 1 plus 5 times 0.11, and we got the answer. We got 67.5 is the accumulated value of Joey's account at time 10. Now we are going to Tina account. Here's the thing, Tina using effective rate 9.15%. So the accumulated function is 1 plus I to the t. So the first payment he's make at time n. So at time 10 is go up 10 minus n step, and another payment of $30 is made at 10 at time 2n. So it's move up to 10 minus 2n steps. So that's why the accumulated value of Tina's account is 10 times 1.0915 to the 10 minus n plus 30 times 1.0915 to the 10 minus 2n. And that is 24 times 1.0915 to the negative n plus 72 times 1.0915 to the negative 2n. And the question said the accumulated amount of Tina's deposit equal to accumulated amount of Joey's deposits. So we are going to set 67.5 equal to this equation. And here we have a quadratic-like equation, but not quadratics. So we set a new variable x equal to 1.0915 to the negative n. We have a new equation, 72x squared plus 24x minus 67.5 is 0. This is a quadratic equation. So we are going to have 2 solutions. However, I'm taking the positive solution, so x should be 0.8158. And when we have x, we should be able to find n. So 1.0915 to the negative n is equal to 1.8158. Take the natural of both sides and then divide by natural log of 1.0915. We have n is negative natural log of 0.8185 over natural log of 1.0915. And the answer is 2.325, which is about 2.3 years. So answer B. So problem 2 is the question of unknown interest, unknown time. So we need to use logarithm for this question. Next, problem number 3. Carl put $10,000 into a bank account that pays an annual effective interest rate of 4% for 10 years. If a withdrawal is made during the first 5 years and 1/2 years, a penalty of 5% of withdrawal amount is made. Carl withdraws K at the end of each of the years 4, 5, 6, and 7. The balance in the amount at the end of the year 10 is 10,000. Calculate K. So here we need to pay attention. We have four at years 4, 5, 6, and 7. We make 4 withdrawals, and at year 10 we have 10,000 left. So that is the money which is ready to be withdrawn. So actually we have 5 withdrawals that at time 4, 5, 6, 7, and 10. You see that? And we need to pay attention one more thing, that is if a withdrawal is made during the first 5.5 years, a penalty of 5% will be made. So at time 4, when you withdraw K, you actually like the account will be deducted K plus 0.05 K, and similar for time 5. So here's how we set up the equation. First, we set V is 1.4 to -1 because the interest rate is 4%, and we use an effective rate. So V is 1 plus I to the -1. Now we consider payment at the end of years 4 and year 5 will be made with penalty. So using comparison date times 0, we have 10,000 is what the money have at the initial time. Then at time 4, a payment, a withdrawal of K is made with the penalty of 0.005 K. And at time 4, we bring to time 0, so we multiply with V to the 4. At year 5, a payment of K with penalty of 0.05 K is made. So we multiply this amount with V to the 5th, because from time 5 to time 0 we multiply with V to the 5th. The next payment at year 6 is K. This payment is made without penalty, so we have K times V to the 6th because we bring money from time 6 to time 0 is backward. And K at time 7 to time 0 we multiply V to the 7. And 10,000, which is the remaining balance, at time 10 we bring to time 0 is become 10,000 times V to the 10. So we have a new equation. And this equation, V is known. V is known. So this equation is just a simple equation of only one single variable K. So we have 10,000 equal to 3.3108 K plus 6,755.64. So solve for K, we have K is about 979.931. So $980 is the answer. So this is the question when some payment, the withdrawals is unknown. Now we go to problem number 4. The present value of payment of $1,004 at the end of 3 months. Here we use months, not years, so pay attention to the time. Is equal to the present value of the following payments. So we have 3 payments, 3 scheduled payments. 1 month from now we have to pay $314. 18 months from now we need to pay $271. 24 months from now we have to pay $419. In this question they give you effective rate. So we are not going to use equated time, but we are going to use methods of logarithm. And the question gives you 5 answers for T. 14, 15, 16, 17, 18. Here T is months, not years. So be careful when you make calculation. So solution. We have 3 payments scheduled at time 1, 18, and 24 months. And we want to combine them into only one single payment of $1,004 at time T. So 1,000, we are going to use present value as the comparison amount. So that is, we are going to use comparison date time T equal to 0. So look at the single payment, $1,004 at time T bring to time 0, it should be 1004 times v to the t. 314 at time 1 will be 314 times v at time 0, and similarly for 271, 419. So first, let's set v equal to 1 plus I to the negative 1, that is 1.05 inverse, and v is 0.9524. So the present value of payment of $1,004 at time t is 1,004 times v to the t, and the present value of the payments shown in the table is 314 times v to the 1 over 12, because 1 month, if we use t in years, then one month later it's just 1/2. T is 1/2, 1 over 12. 18 months later, t is 18 over 12. 24 months later, it's 24 over 12. So the present value of the total payment here is $944.65. Now we are going to set the two present value equal and solve for t. So 1004 v to the t is equal to 944.65. So we have v to the t is 0.9409 and t is 15 months. So the answer is 15, which is B. So that is problem number 4. Now we are going to problem number 5. A loan of 1,000 it make an interest rate of 12% compounded quarterly. So pay attention here. It said the question gives you nominal interest rate, not effective rate, and the loan needs to be repaid with 3 payments: $400 at the end of the first year, $800 at the end of the 5th years, and the balance at the end of the 10th year. Calculate the amount of the final payment. So here the final payment is unknown. So we are going to call X as the unknown final payment. And here, one thing you need to know is the question gives you nominal interest rate, but the interest period is still a year. So we are going to find the corresponding effective rate using nominal rate. So we first find the effective rate of interest I using the given nominal interest rates. So let's say I is the effective interest rate. We have 1 plus I equal to 1 plus 0.12 over 4, the whole thing to the 4. This is using the formula of nominal interest rate and effective rate. So I should be equal to 0.1255, and V should be 1 plus I to the negative 1, which is 0.8885. So now we have V. What we need to do next is bring all the money back to one common comparison day to find the final amount. So here I'm going to choose time 0 as the comparison day. So let's act be the final payment. Using comparison time 0, we have 1,000 at time 0, so it's just 1,000 on the left hand side. Now we look at the payment. 400 at time 1. So it's 400 times V, because from time 1 bring to time 0 we multiply with V. 800 at the at time 5, so we have to multiply with V to the 5th to bring it to time 0. X at time 10, we need to multiply it with V to the 10 to bring it to time 0. So we have this equation where V is known. V is 0.8885. So X should be 1,000 minus 400V minus 800V to the 5th over V to the 10, where V is 0.8885 and the answer is 657.84. So the final payment should be around $658. Next question, problem number 6. You are given delta t is 2t cubed plus 8t over t to the 4 plus 8 t squared plus 16. T is from 0 to 1. That means we should consider at the first year, only the first year. The effective rate of interest I is equivalent to delta t. That means, remember on the first lesson, we make connection between effective interest rate and force of interest rate. So here I is the effective rate that gives the same answer as the force interest rate of delta t. Fund X accumulates with simple interest at rate I, and fund Y accumulated at delta t. So here's the thing, one more thing you need to pay attention. I here is the effective rate of interest that is equivalent to delta t. However, fund X using I as a simple interest rate, not effective rate. So once you find the effective rate I, you have to use the simple interest rate formulas for fund X. Now suppose an amount of $1 is deposited into each of the fund X and fund Y at time 0. So the question is, at what time t is fund X minus fund Y is maximum? So we asking for the time when the difference between two funds is maximum. So and the question gives you 5 choices for t. At 0.25, that means a quarter later. 0.375 of the year. 0.5, that means half year later. Or 0.625 or 0.75, which means 9 months later. So now we are first going to find the accumulation function using the force of interest rate delta t. So remember, a of t is exponential of integral from 0 to t of delta r dr. This is from the first lesson. So inside the square brackets, we are going to compute the integral. So that becomes integral from 0 to t of 1 over r to the 4 ar squared plus 16 d of r to the 4 plus ar squared plus 16. And in the front we multiply 1/2. Here's one thing I want you to know, like if you didn't take calculus 1 and 2 before, I suggest you to learn calculus 1 and 2 before you start practicing for SMFM, because it requires a lot of differentiation and integration. So here I cannot tell you why, because it's going to be a lesson of chain rule and integration. So here for people who have already learned integration and differentiation from calculus 1, 2, and 3, you should be able to know why I have these formulas. D of r to the 4 plus ar squared plus 16 is 4r cubed plus 16r. So divide by 2, you have exactly 2r cubed plus ar. So that's why I'm just kind of break it out to have chain rule, because I want to use chain rule to make it simple. So the integral from 0 to t of 1 over r to the 4 plus ar squared plus 16 d of r to the 4 plus ar squared plus 16. This is just natural log of r to the 4 plus ar squared plus 16. So we have e to the 1/2 of natural log of t to the 4 plus at squared plus 16 over 16, because we consider from time 0 to time t, and that's equal to here 1/2 of natural log. So when we bring 1/2 into the natural log, we have t to the 4 plus at squared plus 16 over 16 taking the square root, so we have t squared plus 4, the whole thing divided by 4. So the accumulation function using the interest rate delta t is t squared plus 4 over 4. Now we are going to use this accumulation function to find the effective of interest rate I. In this question we consider from time 0 to 1. So over the first 1 year, the accumulation function is 1 plus I if we use effective rate of interest. And if we use for interest rate, A of 1 is 1 squared plus 4 over 4, which is 5 4. So they are equivalent. So we have 1 plus I is equal to 5 over 4. So I is about 0.25. Now we are going to use this I as a simple interest rate to accumulate fund X. So fund X at time t. At time t, fund X is 1 plus IT. I is 0.25, so that becomes 1 plus 0.25 t. This is fund X. This is fund X. And fund Y is t squared plus 4 over 4. Here, because we deposited $1, so we don't need to care about the initial amount. The accumulation function is also the accumulated value. So 1 plus 0.25 t minus t squared plus 4 over 4, that is equal to negative 0.25 t squared plus 0.25 t. And we want to find the time when the function is maximum. This is a quadratic, so it's this is a quadratic with the parabola turned downward. So the maximum value should be at the vertex. If you have taken college algebra, I don't need to explain you why the vertex is the maximum, because the parabolas can go downward. So the vertex at the top is the maximum value. So to find time t, we use the formulas of negative b over 2a in the quadratic equation. B here is 0.25 and a is negative 0.25, so t should be negative 0.25 over 2 times negative 0.25, which is 0.5. So the time when the difference between different is maximum is half years later. So you see, in this question, it requires you to know college algebra, pre-calculus, and also calculus 1 and 2, because it requires you about quadratic equation, vertex, and differentiation, integral, integration. So I suggest, if you have not learned, if you haven't taken any college algebra classes or calculus 1, 2, 3, please do before you practice for exam FM. Otherwise, you're gonna see this exam is clueless. Like, you don't know where to start, because many concepts here from pre-calculus, calculus 1, 2, 3, and college algebra. For example, the first slide, you need to learn calculus 1 and 2, at least to know a of t, how to solve for a of t. The second line is easy, but the next line is required quadratics equation that is in college algebra or pre-calculus. So quadratic equation is in college algebra. So you really need to know college algebra to know when the function is maximum. Otherwise, you will have to use differentiation. That means you take the derivative of this equation to consider when the function is increasing and when the function is decreasing to define the global maximum. So that's how you solve problem number 5. So I repeat, if you didn't take college algebra, calculus 1, 2, I think you should take these 2 courses before these 3 courses before you start practicing for exam FM. Next problem. Okay, so that's all about time value of money. And here I also introduced the textbook that I used to make this video, that is study manual for exam FM, exam 2, financial mathematics and financial economics, the 10th edition by Harold Jury and Rick Govert. So here's the thing, even though I'm making this video, but this video is just like summary of the lesson, and I go over some example. But to have the best practice for exam FM, you really need to get this book and go over the practice. So watch my video, you don't have to read the book again, but you still need practice, because without practice you cannot be familiar with the type of question that is given in the actual exam. So please, do not just watch my video. My video is for understanding the concept and also go over some examples. But please get the book, go over some practice to be well prepared for exam FM if you are taking the exam seriously. Alright, thank you so much for watching this video, and I hope to see you guys next video. Thank you, bye bye.